you want to submit handwritten, that's fine, but make sure that there is clarity in your handwriting and all, so that like whoever is checking is the TAs or me is able to read at least clearly. Okay. And you can find like some very nice LaTeX tutorials online. Okay. Good. So also if I said it in previous course also, but I think that does not really work well. That asking students to share their video, keep their videos on, but at least when you are asking a question, please turn on your video. Okay, so that at least I can see that who is asking the question and there can be a more proper interaction. I would like the class to be as interactive as possible. I'll be asking questions. Please answer if you can or want to. I won't be pinpointing people that, okay, you tell me, but I expect at least somebody to answer questions in the class. But don't just leave it on other people all the time. Sometimes you can also participate, and then I'll also see that, okay, this person, and then that will help me remember the names, etc. also. So that is one thing, and that's all from my side before we start with the actual lecture things. So any other questions about the course, about the requirements, about credits? Okay. Another thing I forgot to mention, it's there in the web page. For the most part, we'll be following the book Algorithm Design by Kleinberg and Tardos, and so the name is given there. Indian edition is available for the book. You can buy it, or it must be there in the library also. I have not checked, but it's a very popular book, and that's what we'll be following for the most part. And if somewhere I refer to something else, I'll let you know from where you can get it. Okay. And the lectures will be recorded and they'll be there anyway for your reference. Good. Any questions? Okay. Is there a question in chat or something? No. Okay. I hope you are able to see my screen. So I hope you are able to see my screen, because I am able to see it on my other device. You are?
Yes, sir. It's visible.
Yes, sir.
All right. Cool. So title. So what I'm writing is visible? Yeah, so my writing might not be the best at times. So if you don't understand something, please ask that what is written there. Okay. So are you able to see?
Yes, sir.
Yes, sir.
Yes, sir.
All right. So logistics, we have talked about that it's on web page and everything else. Okay, good. So now the question is, the course is about analysis and design of algorithms. So what are algorithms? The first question that comes to mind. Okay, so of course, you guys would have some idea. Can somebody tell me what is your idea about an algorithm? How can we say what is an algorithm?
Sir, it's a set of instructions to do a given task efficiently.
So efficiently is not really necessary in the definition of algorithm, but yes, you are correct about the. It's a set of instructions. to do a given task. Okay. More than efficiently, I would emphasize the word correctly, right? That whatever the task is, the algorithm should achieve the final, whatever is the desired outcome, right? So, cool. So, we will be looking at computational algorithms, right? So, what are so algorithms are tools to solve, and what these tools consist of will come to algorithmic problems, let's say. Okay. And what are algorithmic problems? Algorithmic problems have a specification of input. Okay. And then they have a specification of output. And now you have to perform something to reach there. And that is the algorithm. So now there is one thing about this specification of input and specification of output is okay. So I'll come to that. Before that, so what is algorithm? So who had answered the question before?
Sir, Amit.
Amit. Yeah, Amit. Yeah. Cool. So yeah, please turn on your video when you answer also. Okay.
Yes, thank you.
Thank you. So as Amit said, it's like instructions, set of instructions, right? So these are generally, since we are will be talking in computational realm, it is going to be outline of a computational procedure. Okay, and in terms of step-by-step instructions. All right. Now there is one thing about this specifications of input and output that I would want to highlight here. So So generally, the algorithms that we'll be dealing with are generic, right? So what does that mean? That the algorithms will be generic. So again, till now everything has been very abstract. As we'll come to more and more examples, they will be like becoming more and more concrete. But since this is the first lecture and we are going to be talking about like the course in general or the concepts in totality, so this is going to be a bit abstract. But if you understand that, it will be good, I feel. Okay, so something about specification of input and output. So one thing that generally happens is that there are infinitely many inputs, outputs, which satisfy the specification. Okay, so what can a specification look like? So for example, input specification can be an array of numbers. Okay, and the output specification can be same array but sorted. in non-decreasing order, let's say. Right? Or the output can be the max of the numbers which are there in the input. So again, an example input can be just 2, 3, 4, 10, 1, 6, whatever. And then there can be another input and so on. And similarly, there can be many outputs also that satisfy. Good. And also in addition to this, there can be infinitely many algorithms. To go from one input specification to an output specification. Okay, good. So what does this mean? That okay, suppose you are given an array, you want to sort it. So there can be many ways to sort it, and like even your way might differ slightly from somebody else's way, and people do things differently. So there can be infinitely many ways to do the same job using algorithms, right? Okay, so now since there are these infinitely many ways to do the same job, how do we select? How do we compare? Which ones are better? Okay. So now we have to decide between which algorithms are going to work better. And any idea? Like you must have an idea. So still,
Sir, order of
So
algorithms.
time complexity and the space complexity of the algorithm.
exactly. So Pratik, you can also switch on your video when you talk, yeah, or you had, and maybe it took time. Yeah.
So we can like calculate the asymptotic time complexity and the space complexity of the given
Yeah, we
program.
come to asymptotic things. So we are building up slowly towards that.
Yeah. Okay.
Right. Yeah. So, all right. Okay, good. So, yeah, as Pradeep said, there are these two resources that we'll be worried about mainly. Okay, which is time taken by the algorithm and space used. Okay, so generally, like how much time the algorithm takes is, so if an algorithm does the job faster, it's considered better. And if it uses less space also, then it's considered better. Mostly we'll be talking about this time complexity. So that will be our primary focus. And sometimes we might even talk about space complexity of the algorithm. So these are called time complexity and space complexity, depending on which resource you are talking about, that how much time an algorithm takes and how much space an algorithm takes, right? But how do we measure these things? Do we just say that, okay, I mean, take an algorithm and, you know, how do we measure
Sir,
the running
number of operations.
number of operations? Okay, good. So let's say running time first. Yeah, let's talk about running time only. So let's say the first idea is number of operations. Okay. So idea number one. So okay, so what does it mean that okay we take an algorithm and see that how many operations it takes, but the number of operations will depend on the input, right?
Yes, sir.
So, I mean, the number of operations is going to vary, right? Depending on what the input is going to be.
Yes, sir.
So, just the number of operations, then how? Like, some algorithm will take less time on some input, some algorithm will take more time on some input. So, number of operations is going to vary. So, then it makes sense that we measure the running time as a function of input size. Right? So what does that mean? That okay, we expect the algorithm to take more time when the input is larger. When we expect the algorithm to take less time when the input is smaller. Like if you are asked to find the minimum or maximum of like 10 numbers, of course you are going to take less time than if you are asked to find minimum or maximum of 1 million numbers. Similarly, if you are asked to sort an array of 10, size 10, then you are going to take much less time than if you are asked to sort an array of 1,000 or 10,000 or something, right? So generally the running time is expected to increase as the input increases. And that is considered a measure of the algorithm's complexity, time complexity, that as a function of the input size, how does the complexity increase, right? How many operations or how much time does the algorithm takes? So also in as you said, number of operations. So number of operations is also an abstraction, because generally what we were saying was time taken, but time taken will depend on like your machine, implementation, etc. Right? So there are these things. So what we will do, we will instead of looking at the actual running time, we will look at the number of operations, because that will give, like, if a machine is doing the operations faster, of course everything will become slightly faster on it in terms of actual time, the absolute time, but still the number of operations is going to be like asymptotically same, or at a larger scale same. We'll come to it that what these things mean, like very precisely mathematically, right? And for that, what we are going to do, so the actual time taken depends on the machine or implementation, etc. So that is why we will, instead of actual time, as sorry, instead of actual time, we'll be looking at number of operations. Good.
I think I forgot to mention here, operations here, we mean basic operations. Because
Yes.
operations can be.
Yeah. So these are going to be basic operations, and like comparison, addition, subtraction, and such things. And generally, we will take care to define that, okay, what are these basic operations. But yes, number of operations is going to be basic operations like comparison, addition, subtraction. Etc. Okay. So the number of steps, basically you visualize the CPU of your computer, like you guys have done. Most of you must have done OS, I guess, or some other course. So you know what a computer looks like, or a CPU looks like, and then there you have these logic gates which are doing things, and so in one step it does something, and that is what basically. So if you want to have a view, I mean, this is not very formal what I'm saying, but just to give an idea that okay, in one time cycle of the computer, whatever the computer does is one basic operation, more or less. Okay, and then the basic operations change according to like different architectures of the GPUs and different makers and so on. That what basic operations do they allow? Because we all know that okay, everything can be done using AND or not, whatever, some three universal AND or not, or some NAND or some NORs. But then using these, of course, like then these can be used to have very complex operations that can be done in one step. But generally, they are like addition or taking or take comparison and so on. That can be done in one step. Okay, so that's what is going to be our basic operations. Okay, good. So there's another thing which is going to be that we'll be using to analyze. So how are we going to count the basic operations that an algorithm makes? So for that we are going to use pseudocode. So whatever algorithms we'll write in pseudocode. Okay. So for example, let's write a simple algorithm for max, finding the max of. So let's say algorithm. So max a n. Okay. And what is the input? Is an array of n numbers, an array A of n numbers, and what is the output? Output is going to be the maximum element of A. Okay. And what is the pseudocode of this? It's going to look like this. Max, you can assign A0, or you can use equality. It, like, it depends on you. For I1 to I1 to n minus 1, do if max is less than AI, then max is AI, right? And finally return the max. So this is your pseudocode of the algorithm. You can put commas just to specify the steps. No, not here. So this is the loop. And so this is just like a programming code, but slightly more informal because the syntax is not like here. I have not written, the brackets and so on. But I did give some indentation to shift it so that you understand what the for loop is for. Like this is the part in the for loop and so on. So this is just like a less formal way to represent an algorithm than a program, and more formal than just like writing in paragraph. Okay. So we'll be using this. So whenever you are asked to do an assignment, then you should be writing your code in pseudocode. So what is the general rule that after looking at the pseudocode, one should be able to write the program in any language they feel like, right? So what the pseudocode will use? The pseudocode will use some programming constructs like if, then, else, and all that. It can have a while loop. It can have for loop. It can have repeat something until, right? And it can have something like arrays, lists, etc. So you can write things like AI or AIJ for, if it is a two-dimensional array, etc. Right? So you can use these things in pseudocode. You can use methods also. So you can define something like and you can call them also. So for example, right now this can be treated as a method of, this whole thing. Sorry. So this can even now be used as a method for finding the max of an array inside another algorithm, right? So these all is allowed in a pseudocode, so you can do that. So if you have done like a little bit of programming, you will know this. But again, it should be clear what you mean. And as I said, somebody reading that should be easily able to convert that into a program. Right? Okay, so that is our thing. That this is how we will be writing algorithms in pseudocode. Now let's come back to the analysis part. Okay, so now we'll look at the pseudocode. And determine how much time it will take the algorithm, I mean, in terms of input size. Right? So again, what is this input size? This input size can be, again, this is a very conventional thing, so this can be the number of bits in the input, or it can also be the number of elements or number of numbers in case it is a list and so on. For example, here, in this case, n is the input size because it is an array of n numbers, right? So let's look at this algorithm and see how much time it takes, right? So the first step is done only once. Okay, so let's use a different color. Once. Now this I is being increased from 1 to n minus 1. So this is happening, sorry, it should be 0. Nobody pointed that out. Oh no, this is fine. 0 is assigned first. So this is done, let's say, n minus 1 times the assignment. So yeah, assignment is also one basic operation which takes time, like comparison, addition, and also assignment, of course. So how do you achieve assignment? You just move one register to the other, wherever you are having the variable. Have you guys done an operating systems course or some programming course? So
Sir, we have
19
done.
batch in.
Sir, we have done
Yeah.
data structures and algorithms only.
Oh, you have done data structures and algorithms. That's good. Okay, cool. So then of course. Okay, so many of these things Then I didn't okay, my bad. All right, so I can speed things up a little, I guess. All right, so but still, these parts are important. I'll speed up when I need to, but this is fine. That from pseudocode, what we do, so this operation is performed n minus 1 times, and for every I from 1 to n minus 1, this comparison is performed n minus 1 times. and this is performed at most n minus 1 times. Because this is not performed all the time, this is performed only when this condition is satisfied, right? So you get at most 3 times n minus 1 plus 1, right? So for max, an, we get at most 3 times and we'll write it as generally as Tn as the running time taken on input of size n is less than or equal to 3n minus 1 plus 1, whatever. Something like this, right? So this is the running time of that algorithm, and this is how we will be doing this analysis given a pseudocode, right? Okay, but so this is the thing that it does on n, and here you see that we did that comparison does like n minus 1 times, and this is at most 3n minus 1, but this is what we call a worst case analysis. So there are 3 kinds of analysis that, okay, so we have this algorithm and we are measuring the running time in terms of input size. But like, how do we, there are different ways to measure, because there are many possible inputs. So how do we measure the running time in terms of the input, in the sense that do we look at the worst case? What does it mean by worst case? That the most time the algorithm can take, or let's say upper bound on the time the algorithm can take on any input of size n. Right? So this happens worst case, that okay, if you give me an input of size n, the algorithm, like for example, this algorithm that we analyzed, the max, it is not going to take 3n minus 1 plus 1 time, right? So this is what we will be doing for the most time. Another thing is average case. One might say that, okay, why are we always doing worst case? On average, the algorithm can be good. Like how much time the algorithm takes on average on average on inputs of size n. Okay. So this actually is, one, there are 2 points about this, that it's very hard to compute generally. And then it's usually or let's say worst case is a good estimate. For it in most cases. Again, here most cases is not a mathematical statement. But average case, and also you would want your algorithm to perform well on all inputs, right? It's not like, good that, okay, on average it performs well, but, if you give the algorithm some nasty input, then it is going to take years, right? Well on all inputs. So for these reasons, we will be more concerned with worst case analysis is what we'll do. There's another thing that is best case, but that is not the best way to analyze algorithm for obvious reasons. For example, if you have already, so what is the best case in the max algorithm? Can anybody tell?
Reversely
Yeah.
sorted array.
2 times n minus 1 plus 1.
Yeah, but when does that happen?
Reversely
When the
sorted
first
array.
element is the maximum element.
Yes, we don't need sorted actually. If the first element is the maximum element, then that's it. You are never going to satisfy this if part, and that is why you are never going to perform this operation after the first operation, right? So that is the best case for this. But again, best cases are like not really useful, so to say. Best case analysis is not like best case is actually useful, but best case analysis is not useful. Okay, so we'll be using at worst. We'll be using worst case for the most time. Good. All right. So now, okay, how much time do we have left? Okay, we have 7 minutes. So I can go till. Okay, so fine. So what is our conclusion from all this discussion? That algorithms that take less time in worst case, because we started our discussion. How did we start our discussion with? We started our discussion with, okay, like there are many ways to solve the same problem. There are many ways to, like infinitely many ways to like get the same input output specifications. Then which one is better? How do we compare the algorithms? Then we came to, okay, there are these uh, analysis like running time we should see and space we should see. We should see which one is consuming less time. And then we saw, okay, how do we measure time? We need to look at basic operations. In basic operations, then we saw that, okay, when should we measure the time? Should we measure the time in worst case, best case, average case? And so after all this, we got to the point that, okay, the algorithms that take less time in the worst case are better. Right? Good. So this is one conclusion that we got for now. So basically what we'll be doing is like, we'll be writing Tn is equal to some f of n where, okay, that does not make sense. Okay, forget it for now. So we'll be writing the algorithm's running time. So let's say A1 has some running time. Algorithm A1 has running time f1n is equal to, let's say, n square, and A2 has running time. Again, now these are, I'm going to talk about worst case only, okay? f2n is equal to n cube, right? So which one is better? Which one is better among the two?
First one.
First one. So this is better, definitely. Okay, so now suppose you have something like, so this was easy. Why? Because n square is less than or equal to n cube for all n integers, right? Okay, but now what happens when it becomes something complicated? Suppose you have n square and then you have n cube minus like 50 n square minus 1000. Okay. So which one is better?
The first one.
If we talk about asymptotically, then first and third will be equal, and
Okay, so I want to actually, that's what I want to build up to asymptotics. That okay, why is the first one better? So like without using asymptotics, can somebody say or like
without using asymptotic, we
Sir,
can
for
say that
large values,
third will be better.
say sorry?
Without asymptotic, we can say that third one is better than first one, and first one is also better than second one. So order will be 3, 1, 2.
No. This is one running time. Sorry, there is no third one. What is third one?
Okay.
So these are
NQ minus 50 and n square minus this.
yeah, and NQ minus 50 n square minus 1000
okay.
is one.
Okay, sorry.
Yeah.
Then we can say that n square will be better than n cube minus 50 n square minus 1000, because we
Why?
can find we can find for a large n, we can say that this n cube minus 50 n square minus 1000 will be greater than n square.
Yeah. So okay. So Nishant is right that actually, but for many inputs of smaller size, this will be better. Sorry, this will be better. But this will be better for larger size. And this is what we want to somehow give a formal definition of that. Okay, what is this? Because we are generally interested in large inputs, that how the function grows. We are not interested in, okay, initially there will be, so if you look at the graphs, initially there might be some this thing, but above, so here there might be a lot of overlaps and so on, but suppose it happens like this, then this algorithm is better, right, than this one. Why? Because after this point, it always stays below. So if we can find such a point that such that this stays below, then it will be considered a better one. So let me just leave you with the definition of asymptotic upper bound. Okay, and then we can come back to it tomorrow. Right. So what is the definition? So let Fn and Gn be two functions. We say that Fn is equal to big O of Gn if there exist constants C and N0 such that Fn is less than or equal to C of Gn, C times Gn for all n greater than or equal to 0. Okay, and we say that Fn is asymptotically upper bounded by G. Okay. So this is just the definition of and since most of you guys have done the data structures and algorithms course, you are familiar with it. So at the risk of repeating it, I'm giving the formal definition, but it is going to be very important because we will be analyzing the running times of the algorithms of all the algorithms in this class using asymptotics. So it is very important that you get the definition, you get I'll also be giving some assignments of the on this, and so that you get used to some comparing the running times, etc. And yeah, so this is the definition of. So what does it say? That if there exists a constant C such that if you can multiply C by this multiply G by this constant, and then there exists a N0 above which you can get this. So this is Gn, and this is Fn. Then Fn is less than or equal to Gn. Here the constant C is 1 in this graph. And then above N0, and then we get that Fn is at most is asymptotically upper bounded by Gn, right? So in the next lecture, we will also see what is asymptotic lower bound and how they are related, and some other properties of these big O notation, which again, like you might have seen before, but it will be good to revise. And I've taken like slightly more time, so we have time for a couple of quick questions if somebody wants to ask.
Sir, there was a little doubt. Like,
Yeah.
is Fn belong to order of Gn, or it is equal to O of G of n, like in the definition?
So we say that we'll be using Fn is equal to order of Gn. So this equality is not really equality. So it is slight abuse of notation, but this is how it is done in, like, you'll find.
Sir, number theory usually equal to is used.
Say again.
In number theory, usually we use the equal to sign.
In number theory, you use which notation?
This one, equal to.
Equal to, yeah. So again, it's a conventional thing. Of course, I understand that you are saying that big O of Gn is a set of functions which actually is a set of all the functions which are asymptotically upper bounded by Gn. But in this course and in like in general algorithms, we'll be using this equal to notation. Okay. So it's, I mean, you're right in saying that it belongs to, that it's a set, but we'll be writing it as equal to Gn. Any other question? Or, I mean, yeah. Just a moment. I'm just checking with the book if, like, they say it explicitly or. Yeah, Tn is equal to order of n. They say that. Yeah, so this is a slight abuse of notation, but I think this is fine. This will be clear from context. Any other question? Okay.
Excuse me, sir.
Yeah. Yeah, tell me.
Also, like, could you give an example of an algorithm where the function Tn isn't really monotonically increasing or decreasing, like the cubic polynomial which you just used? So, like, are there really algorithms which have such Tn functions?
I mean, one can design. There are infinitely many algorithms.
But like, still, how would one design such an algorithm which takes more time for n equals to 50 than 25, but lesser time for n equals to 100? So, like, how is this kind of possible?
It depends. That algorithm might be for problems which, again, like, it's just, you never know, or even the input specifications can be that, okay, only for prime numbers I need something, only for even numbers I need something. Like, that depends on the specifications of the algorithm, right? So suppose, can you imagine that, okay, an algorithm takes more time for prime numbers than for, composite numbers?
Yeah, like.
Yeah. So all I'm saying is that it depends on the specification. Again, these things are cooked up, but the thing that we will come to is that actually these things are not going to matter later. And we'll show that in the next lecture, that generally just the higher order term is what is going to matter. So we are formally going to actually build a like framework where actually those things, such things can be ignored even if they exist. So you are right in saying that mostly they would not occur, but there can be instances when they occur, but we are being formal so that we can ignore them even in those cases.
Yeah, sir. Thanks.
Okay. Okay, any other question? Okay, so yeah, we are over time. So yeah, see you guys on Thursday. And yeah, thank you for coming today. See you.